For a while now, we've been focusing on data structures and abstract data types. That is, we've been talking about ways to store and represent information. This chapter is a bit of a departure from that. Rather than talking about data, we're going to actually introduce a new kind of mechanism that we can use to solve problems. This will give you a whole other approach to problem solving. The general term for this method is called recursion. So recursion is the following idea. Define a problem in terms of itself, or define a solution in terms of itself, right? Rather than having an algorithm that looks at its problem and it does some work, maybe has some loops, calls some methods, and it goes through and it just essentially solves the whole thing outright. What we want to do is you want to think about solving problems in terms of making them a little bit simpler. Meaning we have a problem, we do a little bit of work, and inside that problem we find a sub-problem, right, an inner problem. And that problem we can then attempt to solve that as well. So it's a problem that's inside of another problem. At this point, this may seem a little odd, but we've actually already used this general concept of recursion. So think back for a moment to the coverage we had on linked structures. In linked structures, we implemented nodes, and nodes contain a reference to another node. They're what we call the self-referential data structure. That is actually recursion, right? Every node contains another node. So we've already seen this idea. Of course, things get a little bit more tricky when we start to try to apply this in terms of an algorithm. But for a data structure, it's already something we've seen. So let's spend a little bit more time talking about that. So over here, I have kind of a very simple list, right? And I'm not using the notation I typically use, right? This is kind of the slides notation. But over here, right, we have a list containing 4 elements: 24, 88, 40, and 37. So we have these here. And maybe you could even picture, right, maybe we make this look a little bit more like our previous notation. Each of these, right, is a little box, maybe. And each of them, right, is going to be connected to the other ones, right, in kind of a linear fashion. So we'll just do this very simple diagram. I'm not going to kind of make it look too fancy. But we can think of this in the following way. A list, right, it contains a bunch of elements. A list is really 2 different things, or can be 2 different things. A list could either be a single number, right? So picture a node where next is set equal to null, so just one thing by itself. Or it can be a node that contains a number followed by another node, meaning another list, right? So I can visualize, right, this picture up here as this being a node followed by a list. So this is kind of, there's 2 lists here, right, in this picture. We have one big list that contains the front node, and then that node, right, is linked to another list, right, the tail of it, the rest of the stuff that's inside there, right? So we have this outer list and then this inner list. And in between, right, there's this one node, right? So this is simply another way we can think of our data structure, right? We have a list inside of a list, right? Of course, right, I kind of went through it fast, right? But in addition to a list being a node followed by a list can also just be one node, right? Nothing coming after it. So this is a recursive structure, right? A list contains a list. And if I look deeper, right, if I look at this inner list here, the 88, 40, and 36, I'll realize, oh, hey, it's the same thing. I have a node in front followed by a smaller list inside, right? So we have lists inside of lists, a self-referential data structure. Now, the next slide actually breaks this down in a little bit more detail. So initially we have, right, that list of the 4 elements. And what we said is, hey, it's a list, which is a number, followed by another list, right, a slightly smaller list. And in the notation here, because we're not using kind of the square blocks I normally use, we just have a comma here to indicate that, oh, it's something followed by some other stuff, right? So a number, this list here, right, of 4 numbers is a number followed by a slightly smaller list. And that process repeats again. So this is a list. How do we break it apart? How do we see what's inside? Well, we take off the 80, right, the number in front. We say, oh, well, hey, it's a node that for 88, right, followed by another smaller list, right, now of 2 elements. So this one up front, this stuff here in the back. And really, right, this whole section here, right, this little slightly smaller list, right, is how we're defining this chunk here, right, for this list we broke off on the kind of the first step. And this repeats again, right? So I have another list inside of here, right? So now I have a list of only 2 things. The first thing being a 40. And then it's followed by another list, right? Now this list is very small. It's just one thing, a 37. And they're separated by a comma. So this goes inside of this, right? This is me just, again, I'm breaking down this list, right? I started as a very large list. It was a number followed by a list, and I'm keep on looking inside that list, inside a list, inside a list, and I'm breaking it down, right? It's a recursive data structure. A list is made from a node and a list. But then we get kind of to the ending point, right? I have only one thing left here. If I kind of did the same thing and said, oh, a list is always a node followed by another list, then I would keep on going, right? There would be another node, another node, another node, another node, another node, right? There'd always be some number in the front there, and there'd always be a tail after it. Well, there is kind of a second condition, right? We said, oh, in addition to a list being a number followed by another list, there's a second case, right, where a list may also just be a number by itself. This is what we call the base case, right? This is a term you may have heard in discrete math when they talked about induction. This is sort of your stopping place. This is a list by itself, right? A list of one number, and it doesn't have anything after it, right? It doesn't have another list after it. It's just made of one number, right? Because we need some place to stop. We can't just keep on going. So this is this over here. So this is kind of a breaking it down approach, right, to seeing recursion, right? Data structures, right? The lists we've been talking about are recursive, right? There's lists in front of lists, right? That sub list, right, again, that's represented in the code you've written before as the next variable, right? The thing that comes after the nodes you're currently looking at. Just what is still remaining. The part here at the end where we said, hey, a list can just be a number followed by, nothing else, that's actually a very key thing here, right? If we don't have that, our list goes on forever. And that is actually called infinite recursion, right? We need to have some sort of stopping place. Otherwise, we're going to keep on building. Or maybe you can picture, right, if I was coding something and I had, for example, a method that called itself, I would want to make sure that it doesn't call itself forever, right? It'll get stuck there, right? It'll never return and give me back my answer. So we want to avoid that, right? We always want to have some stopping case, right? Or base case is a general term. You may also hear another term is stopping condition. And I think there's a few more, although I don't remember them off the top of my head right now. For this class, we're going to use the term base case. So a key point here, if I wanted to find something in terms of itself, I need to have kind of a two-part rule. One that, yes, I'm allowed to do that, right? Define myself in terms of myself. But then I need a second rule, a stopping rule, right? Where I don't talk about myself again, right? I just kind of end it there, right? I just say, oh, there's just one number, there's just one node. Otherwise, it goes on forever. I know this is still a little bit abstract for you guys, so we're going to kind of do this in layers, right? So this is an example in terms of data structures. Now let's look at mathematical formulas and something you've probably seen before. So this is factorial. There are quite a lot of mathematical formulas that can be expressed recursively. Factorial is an example of something that's very commonly expressed as this recursive function that relies on itself. So the idea of a factorial, right, is that you have some number and you want to take the product of that number down to 1, right? So if I have the number 5 and I want to do 5 factorial, then I need to multiply out 5 times 4 times 3 times 2 times 1. That's the basic idea of factorial. Take something and a bunch of products till you get down to 0. Well, it turns out there's a very easy way to write this in terms of just the mathematical expressions. And that's what we have over here. And this is a two-piece equation, right? Maybe you can think that it would be better written as a piecewise, but here we're just kind of doing it on separate lines, so it looks almost a little bit like a program. So 2 rules here, right? If we want to compute that factorial. The first thing is we have kind of our base case, right? The place we stop. So the base case, or maybe another way you can think of this is that the base case represents the simplest version of the problem, right? So it's so simple you don't need to solve the problem again, right? You can just stop there. You don't need to do any other work. So the simplest thing we can do, right, in terms of factorial is take the factorial of 1, or you could also use 0. But the point is, for factorial of that number, right, factorial of 1, return 1, right? That's what this first line is saying. Factorial of 1 is 1. On the next line, we have the more complete rule, right, which is a recursive step. So a recursive rule here is saying factorial of n is equal to n times n minus 1 factorial. So notice here, right, that this little symbol here, right, the explanation point that I'm writing as factorial, that's occurring on both the left and the right-hand sides. So the way I compute factorial of n, right, is defined in terms of another factorial, right? That's a recursive part, right? We're defining something in terms of itself. So if I want to compute factorial, I have to compute n, right? Or, well, I don't really have to compute n, but I have to get n, and then multiply it by factorial minus 1, right? So a slightly smaller factorial than the one I began with, right? So if I was doing factorial of 5, say if I have this, right, factorial of 5, that's going to end up giving me, all right, if I follow this formula, then I'll need to figure out this. 5 times factorial of 4, right? This is my recursive bit, right? My factorial is defined in part in terms of my factorial. Of course, you may be wondering, oh, well, how does this thing ever end if you always have a factorial there? Well, what you do is you just apply that rule a bunch of times, right? So here, right, if I maybe started to write this out, and we'll do it a little bit more on the next slide, I could actually write this. 5 times factorial of 4 equals 4 times factorial of 3 equal 5 times 4 times 3 times 2 factorial, and so on, right? The idea is I can keep on expanding out that little bit of factorial that I need to compute, right? I just apply that rule again and again and again. And then eventually, right, I'll get down to the simplest case where I don't need to compute a factorial again, right? Once I get down to 1, I'm just done. So this is a kind of a classic example of recursion in math, right? And this is mainly coming from the fact that our idea of recursion, right, producting all these things, it's very easy to think of it, right, in terms of recursion.